We've learned how to evaluate definite integrals by either finding the area between a function and the x-axis when given a graph, or by finding the antiderivative of basic functions when given an integral of a function. Today our learning target is to learn a new integration technique called substitution, which allows us to evaluate definite integrals using substitution by changing the variables. And while this might at first seem like a complicated process, its purpose is actually to simplify an integral to find the antiderivative. And because we have to change the variables during this process, we therefore have to change the limits, which are controlled by the variables. And I'll explain all these steps when we get to an actual example. But in short, substitution is used to basically undo the process of the chain rule when we use it in the forward direction of derivatives. So here's a list of integration techniques that we're expected to know for the AP exam, the first three of which we've already been practicing, and the fourth is the new one for today with the substitution. So the first says formula. So these are integrals that you're supposed to recognize right away that you either need to use the power rule, it's an e function, a natural log, which is the exception to the power rule, and either a trig or an inverse trig formula that you can apply. The second technique is to use area to evaluate the integral, and this is done when we are given a piecewise graph so that we can find the geometric shapes. An absolute value function can be used finding area because it creates, again, geometric shapes. And not as often, but a square root function sometimes gives us a perfect either semicircle or quarter circle, so area is a good option for that as well. Our third technique is just to use algebra to simplify an integral that at first looks complicated, but might be easier if we distribute a function or if we reduce perhaps a quotient. So sometimes that is a good option that people often forget. So keep that in your toolbox. And then today's new technique is called substitution, and I mentioned it's the reverse of the chain rule. And it's used specifically when the chain rule has an inside derivative that contains a variable. To explain that concept a little bit further, I'd like to look at these two examples side by side. I tried to make them look very similar to each other with just a slight difference. And you'll see that one is labeled no substitution needed, where the other one says that substitution is needed. So let's talk about why and why not it would be needed in either situation. So if you look at the inside function for the first integral, we have 4x minus 3. The chain rule for that would just be 4, which is a constant. It does not have a variable, so we would not need to use substitution for that. Whereas if you look at the second integral, although it's very similar, the chain rule of the inside function 4x squared minus 3 would be 8x, which has a variable. And that's the distinction on whether we need to use substitution or not. So let's solve the integral that we already know how to solve because it does not require substitution. And really this is just a power rule integration with chain rule involved as well. So when we go to set up our antiderivative, we know that 4x minus 3 needs a new power, which we get by adding 1 to give us the third power. And we divide by that new power of 3. And then the chain rule says, if you have a constant chain rule of 4, we are going to divide by that 4 because when we go forwards, the chain rule means to multiply by 4. So going backwards, we have to do the exact opposite. And since we're already dividing by the new power 3, we're also dividing by 4. It makes sense to just go ahead and multiply both of those in the denominator from 0 to 1. When we started our evaluation step, you'll notice that I went ahead and multiplied the 3 and the 4, and that gave me a denominator of 12. I'm plugging in my upper limit, minus, and then plugging in my lower limit. So according to the fundamental theorem, calculus part 1. And after doing my evaluation, subtracting and simplifying, the final answer would be 7/3. So as we try the first example where substitution is needed, I would like to go through the steps one by one, explain each step as we perform it in the example. The first thing we need to do is define our u, which is the variable that we're going to substitute in to simplify the integral. And u is usually the inside function. So for this example, it's 4x squared minus 3. If there's not an inside function in your integral, it could be that u is a function whose derivative is also present in the integral. And we'll see that in our third row of examples, and I'll talk about that a little bit more then. So once you've decided what u is going to be, you find the du dx, which is the forward derivative of x, of u, which is 8x, and that's something we had already thought through by checking the inside chain. And to get du by itself, I simply multiply both sides of that equation by dx, so you get 8x dx. So I've completed my setup for the u substitution. I've gotten my u and my du identified, and those are what I'm going to substitute into the integral, meaning I'm going to have to find a match for both of those terms exactly. So let's talk about how we can do that with this integral. I can clearly see that I have this 4x squared minus 3, which represents u, and that makes sense because I picked it out of the integral. The one that's harder to match up is the du that you come up with. So I see that it has 8x and dx. I see that I have an x and a dx. They're not together, and I'm missing the 8. So I've got to do a little rearranging and a little bit of clever mathematics to make that work out. So what you're seeing here is I've done a little bit of rearranging by moving this x back with the dx, and I left a space because I'm going to need to insert the constant, which is 8, to make it match up with du. Now I can't just put a constant in an integral because I want to. I have to do it without actually changing the value of the integral. And so the clever way to do that is actually to insert an 8 over 8. Now that I have expressions that match u and du perfectly, it's time to substitute u and du into the integral and change the limits. So you'll see this expression will be replaced by u. It is still squared. This 8x dx will be replaced by du. And then the constant that we had to use to get our constant will be factored out of the integral, using that property of constants of integrals to give us 1/8 in front of the integral. The reason I have to change my limits is because in the beginning of the problem, these limits were x values, and now my integral is in terms of u, so I need to turn them into u values as well. And the way that you do that is you take your lower limit 0, and you actually plug it into x in the u function. So 4 times 0 squared would give you -3 as your new lower limit. You do the same thing with 1, your upper limit. 4 times 1 squared minus 3 would give you 1. So you've now converted your limits to u limits. So now that our substitution is complete, I hope you can agree that although it took a few steps to get there, this integral that we ended up with is a lot simpler than the integral that we started with. In fact, our next step is to find the antiderivative of just u squared du, and that really is just a power rule on the u, which will give us u cubed over 3. It's important to notice that we are still keeping that 1/8 constant in front of our antiderivative, and it will stay in front of our last step, which is to evaluate the integral using our limits. So the fundamental theorem says plug your upper limit in first minus your lower limit. And once you plug those limits in, subtract, and reduce, your final answer will be 7 over 6. Let's look at the next set of examples and talk about why one of them does not need the substitution, the other one does. With trig, it helps to write in your own parentheses to see that inside function. So I see on the left my chain is 2, which is just a constant, and on the right my chain is 2x. So that is going to require the substitution. So my u will be that inside function of x squared. My du will be the chain 2x times dx. And if you're comfortable, go ahead and try that and check the key. And this is where we'll pick up in class together.